the REWIRE expert interview series in which we talk about security within IoT environments in the context of zero trust systems of systems. REWIRE is a visionary 3-year project funded by the European Commission under the Horizon Europe program. The project envisions a holistic security management framework to safeguard complex IoT ecosystems during the whole spectrum of their life cycle, from the design to the runtime phases. My name is Christiana Kiperunta from 8bells, one of the partners of the REWIRE consortium, and I am delighted to introduce our expert of our 6th interview, Samira Briongos from NEC Labs Europe, one of the technical partners of the REWIRE project. Welcome, Samira, and thank you very much for joining me today.
Thank you very much for the invitation.
Can you please explain what is the most urgent problem in cybersecurity research that you are trying to solve in REWIRE?
That's kind of a tricky question because there is not one problem that is more urgent than other. The moment you have one issue with cybersecurity, everything is kind of broken. But in the context of REWIRE, we have many devices, many heterogeneous devices kind of distributed, and we have chosen the architecture and the hardware and the software that allows us to kind of have control of everything. The problem is based on the architecture and how so we are using RISC-V, and based on RISC-V you have different level of privilege. One is like this, like the security monitor, and then you have like the normal applications and the normal operating system on top of that. This privilege mode is the one that gives you access to everything basically. But still most of the applications run outside, and they need to communicate to make use of the resources that the security monitor is exposing. So what we are doing here is basically trying to make sure that the untrusted application can access the security services provided by the security monitor. They can communicate data, and everything kind of works according to the specification.
In this context, in REWIRE, you are working on one of the core trusted computing building blocks towards enhancing the operational assurance of smart systems, which is runtime attestation. Could you explain us the philosophy behind trusted computing, attestation services, and the novelty that REWIRE brings?
Yeah, sure. So when we talk about trusted computing, we are talking about the foundations of both the hardware and the software components that will give what we call a secure system, or at least a theoretically secure system based on these specifications. And there are working groups and so not just for RISC-V, for everything, for different applications that establish what are the requirements for a device to be included in one of those trusted devices. So when we say trusted computing or at least the root of trust and these things, we basically refer to all the hardware and the software that need to be working and need to be working correctly to provide all the services to make sure that no information is leaked and that the device operates properly according to this specification. When we talk about attestation services, we just refer to the procedure to make sure that the device says it is. So for example, if I have one IoT device, it is assigned some cryptographic material, and based on this cryptographic material that this device is already holding, it can prove to other devices that it's really this device. This is for the device, but you can also do the attestation of the software stack, and the procedure is basically the same. So based on this hardware that you already trust, you kind of extend the keys and everything to make sure that it applies to the software you are trying to prove you are running. So in the end, after the attestation procedure, you can demonstrate that both you have a hardware device that you can trust and a software stack that you can trust. In the case of REWIRE, we are also providing runtime attestation, because in general, when we talk about attestation, we refer to attestation at boot time, so when the device starts and the programs start. But REWIRE has managed to kind of add some hooks to the program, some gadgets that allows you to kind of interrupt or collect some information from the programs when they are running. So you can also provide this information as part of the attestation. This information is signed with the keys that we derive from the hardware, and then you do not only prove that the hardware is correct, the software is correct at the start time, but also it's running correctly.
Samira, you're currently expanding to the RISC-V type of hardware, and can you please summarize what are the unique characteristics of such open hardware solutions? And of course, what are any other challenges that these pose when designing and implementing your attestation safeguards?
We are really working with RISC-V solutions, but we are not really touching on the hardware. So we are expanding on the software that runs on top of these hardwares to make the whole ecosystem grow and offer more services. So it's not that the hardware can grow without the software and the other way around. In the case of RISC-V, so it's common that people know about the x86, the normal Intel or AMD processor we have in most of the computers, also ARM, that are on the phones, usually on the smartphones. And RISC-V is kind of another way to specify the instructions that the processor is going to execute. But the designers or the founders of this architecture, this ISA, they decided that they are not going to charge to anyone to use it. So for example, if you want to design your own processor in ARM, you can buy a design from ARM and customize it, but you still have to pay some fees. In the case of RISC-V, you have access to all the specification of the instructions, what they should do, but you don't have to pay any fees. So you are free to implement whatever you want. Also, you are free to expand the number of instructions you want to have there. This freedom also applies to the software. So it's not that you are given a software that runs on this RISC-V CPU. You will need to kind of implement your own, or at least customize whatever is already available. So these are the unique characteristics of RISC-V. If we talk about challenges first, since we are not really hardware designers, we need to still trust on whatever other people has done. This means that we need to, or we should analyze whatever the processor are doing, and also because it's still a growing architecture, growing ecosystem, the solutions are not as stable as other solutions. For example, when we talk about TEs, there are open source designs for TEs that you can build on, that you can customize, but they are not bulletproof. That means they have errors, the documentation is scarce, and these kind of things. So this is what we kind of have to deal with in REWIRE.
So you mentioned TEs. Can you elaborate a bit on them and how you are considering them as the root of trust in REWIRE? Does it offer any unique characteristics in comparison to other community TEs?
I should have maybe said before what TEs are. When we talk about TEs, we talk about trusted execution environments. It really means that we know how to protect the software when it's at rest, or when it's stored in the hard disk in your computer is not running. You basically encrypt the whole hard drive and that's it. You decrypt it with your unique key. We also know how to protect data when it's being transferred between two devices. So when I'm sending you an email or when I'm communicating with you in any other way, usually the communication is encrypted. But these came to offer a solution to protect the data when it's executed at runtime. That means when you are running your program. So when you are executing your program, usually the operating system is more privileged than the normal applications, and they have some privilege to read into the data that it's being processed by these programs. So if you are outsourcing data in the case of, for example, cloud computing or environments like this, you don't really trust the operating system and you want some further guarantees on your data while this data is being processed. So this is what these do. They basically isolate this data in some protected area in the CPU, and this data cannot be read nor by the operating system nor by any other application, so just by the owner of this application. So this is what these do in general.
Sorry, go ahead. Yeah.
No problem. And if we try to compare them with other architecture, like what you say, SGX. SGX is a proprietary solution from Intel, and there you can only use the primitives that they give you. So if you want to use Attestation, it has to be through their service. If you want to implement or increase the size of the enclave, which is the name of is another name for the TE, you cannot, because it's given by Intel. So they impose you some constraints, but they also are supposed to give you some guarantees in case something breaks.
What I wanted to ask, in REWIRE, are you considering the extension of your attestation capabilities through instruction set architect extensions?
No, as I said before, we are not really touching the ISA. So we are just expanding on the software. So the idea is just purely based on the specification, on the instructions that are public and they are independent of the implementation. So you can have many manufacturers implementing the same specification, and these instructions have to be there. So just purely based on these instructions, we are trying to build the solutions on top of that to make sure they are compatible regardless of the manufacturer. And expanding the instruction set, it's done in the case of RISC-V, is done through different working groups. And these working groups have periodic meetings, reach agreements, and this is not what we aim to do, at least not for REWIRE.
What types of attacks can such solutions protect against? Considering also recent attacks that aim to use software to exploit hardware vulnerabilities, to steal sensitive information, bypass protection mechanism, or even compromise the entire computer system. What types of computing platforms are affected by such attacks and that you're trying to safeguard?
Yeah, maybe I start from the last question so I can be on top of this. A couple of years ago, side channel attacks became quite popular. Basically based on the design of the CPU, some researchers were able to see some information that shouldn't be there. Basically, when we talk about speculative execution, we are talking about the processor trying to make the most out of the cycles. So they were basically executing some data or some instructions even before these instructions had to be executed. That means if you were accessing a secret, they were thinking, okay, this secret is going to be accessed in like 3 cycles in the future, so let's start to access it now. And then if the information is not used, we'll just roll back the software state to this point. The thing is, they did it for the software, but they couldn't really revert the hardware stack. So if you create side channel, so some contention in this resource, you can figure out what information was being accessed by the victim in this case. So this is based on the hardware design, but can only be exploited through some software created side channels. So here in REWIRE, we would like to protect from this side channel, but for this we just need to select some CPU cores that are not vulnerable to these attacks. So if they do not implement speculative execution, then they are not vulnerable to speculative execution attacks. But there are other kind of side channels, like power side channels, that basically you measure the power consumption of one device while it's manipulating or operating on some secret data. And based on this data, you collect some measurements. You see whether the data is 0 or 1 or so you can guess the secret. Generally, you consume more power when you need to switch some data on than off, and inside the CPUs. So we in REWIRE, as I said, we are protecting for some cryptographic operations from power analysis, and also from not from all side channel attacks, because we are not touching the cache design, we are not touching some of the internal designs, but for speculative execution we have selected one of the cores that do not implement this kind of features, so we are theoretically safe.
Based on what we have discussed, it becomes apparent the importance of security mechanisms as part of the overall hardware security. So in general, how do you think that REWIRE solutions can impact the overall industry, targeting the deployment of heterogeneous devices as part of safety critical infrastructures?
We've already discussed a little bit about attestation. In the context of REWIRE, we aim to guarantee that all the devices are in a good state, and also that the code that they are executing is in a good state. So if you can just make sure that all the devices from whatever company or industry that have been deployed for, I don't know, controlling one factory or the safety system in the car, you kind of make sure that the car is more secure, or at least it's running in a known state, so you know what is happening at every time, or you should be able to know what is going on at every time. And the moment you detect some deviation in the behavior, then you can quickly correct this error and fix it. So I believe it's a good solution for such heterogeneous and distributed systems.
Okay, let's talk about sustainable security. Security with longevity. How the technologies of REWIRE can help towards sustainable security? Is it enough, considering also the need to converge with safety?
If we just consider sustainable security as security with longevity, then I think REWIRE is a good solution. Just let me clarify this. So we are saying that REWIRE solution is purely based on software. So we do not need to expand on the hardware to provide our security solutions. We are just using the software, and it's way easier to change the software than to change the hardware. So basically the hardware you cannot change. So once the device has some specific hardware, you cannot really change it. Maybe if it's a super advanced device and they are implementing some microcode patches, so for this the device has to be able to deal with microcode, not the ones we are using in REWIRE, because those are more target for IoT applications. Then it's clear that having a solution that purely works on software makes it able to deal with new or possible security issues, rather than if it also relied on the hardware. And regarding safety, so for safety, again, you need both things. You need the hardware and the software. If the hardware fails, it doesn't matter if the software is correct or anything, the device is going to fail no matter what. So for safety, it will allow you to detect when the hardware is also not working, because we have included some mechanisms to detect misbehaviors in the hardware too. So it will help with safety, but not solve any safety problems that we find.
Considering that we are getting closer to the end of the project, are the goals that you had in mind, that you have set from the beginning, as it pertains to the design of adequate security schemes, been achieved? And what kind of challenges have you faced?
I will say most of them have been achieved. Not sure if all of them. Well, some of them are still work in progress. We are still working on providing some, on expanding on the solutions, for example, for the communication of information between the untrusted applications and these privileged entity like the security monitor, and there are still things that can be done. But I would say I'm mainly satisfied with the results we have achieved in REWIRE. About challenges, so the project started a couple of years ago, and as I said before, RISC-V and the ecosystem is still growing. So we decided to start building on top of one existing solution called Keystone. Keystone is a software solution to implement TEs on RISC-V. And the thing is, the solution was working, it was promising, but there was a lack of documentation. There were some updates on the code that were not really documented or explained. Again, also it happened when we have already started to work with the previous solution, so we had to rechange all the software stack we had. Since again, it's an open solution, so there are open and available cores, but those cores are like soft cores. So soft cores is just the CPU, but built on a hardware language, so you can just synthesize it on an FPGA. If you compare the performance of these FPGAs with a core, with a normal IoT device, which could be like a Raspberry Pi, the performance difference is quite huge, and in this case the FPGA is kind of losing one. So if we try to make it work, the FPGA, for some of the use case partners, to implement the solutions not based on top of what we had, on top of the security solutions we were offering, but it was not really working for all the cases. So that was another challenge that was solved by, for example, selecting a different board. That we were lucky that some other manufacturer managed to just build a whole CPU core in silicon that made it faster, and also it made the peripherals already available for the RISC-V ecosystem. So they basically wrote most of the drivers and those things that you would have had written on your own in the other case. So we got lucky in that sense.
Samira, thanks for sharing this. And before closing our interview, is there anything else about REWIRE that you would like to add?
No, so overall I think the project has been developing quite nice. I think the project has found really nice use cases to showcase that the RISC-V ecosystem is a good solution to fit all of these use cases, that it can be adopted. You can save money by selecting this and not having to pay for the CAN in the other architectures. Also, that you can reduce consumption because those RISC-V processors are intended to reduce consumption or to use as low power as possible. And it also showed that we can kind of listen to the needs of these, on the research part, we kind of listen to the needs of these industrial partners and try to find the best solution for all of them. And that brings me to the modularity, which I think it's a good thing to have in every solution, not only in REWIRE, but REWIRE is taking advantage of it. So I think overall, or just to sum up, that REWIRE offers a nice solution to provide some security features, some extra security features to different industries, and covers their needs in a, I would say, satisfactory way.
Samira, many thanks for being here with me today, and thanks for sharing all of this information and insights from your side and from NEC side. Thanks a lot for this.
Thank you.